It's good to be here, and let me start. So do you have my slides?
Yes, everything is fine.
Okay, perfect. So let me start. Okay, we have a project for multi-domain text classification that we are doing many different machine learning teams on this topic. And as you can see here, we used uncertainty in this case to handle multi-domain text classification. And this research is done in RIKEN AIP, as I mentioned before. So we all use text classification. We all use it every day and in different forms. So we use it for news portals use it, vertical search engines use it, email providers use it. We use it for market research, for author identification, whether this text belongs to this author or the other author, whether it belongs to Shakespeare or other authors. Is it real or fake? Or we use it for trend detection in social media, and we use it for multiple domains, and they have different vocabulary, grammar, writing styles, collocations, and different things. But the one thing that they all have in common is that they are all using English or same language as if you care. So a better way to handle all of these individual tasks, as you can see, we have task 1, task 2, and task n. We have many different tasks that are working on top of English and doing text classification, is that we can use multitask learning for them. So what is multitask learning? Multitask learning is the type of machine learning that tries to use commonalities and differences between different tasks and exploit them in order to get better results. And in this case, most of the cases, we want to find better features using all of these tasks together. It has many different benefits, but it has its own challenges. So let's talk about different ways of doing this multitask learning. So in multitask learning, you want to share different parameters in a deep neural network between different tasks in order to use their cumulative knowledge to have some features or a group of features. So we can have those features, as I mentioned in a previous slide, like in full share, all of the features are shared, or we can have some of them as shared features and some of them as private. We can share the memory. The task could be hierarchical. Then we can use cross-stitching. We can use routing. We can use partial features. And this is a hot trend, so many people are trying to come up with new ways to use these features and share these tasks. And in computer vision now, it's very somehow very hot trend, and most of the awards of the best paper awards are going into this domain. And in NLP, it started to kick off as well. And it started to rejuvenate. So a few years ago, it was hot. And so the benefits of deep learning is that you can use this multitask deep learning is that we can use it to improve learning efficiency and to improve the prediction accuracy of your task. So you have one task and it has limited number of data and you have limited number of samples, and maybe it doesn't handles all of different grammars, all of different vocabularies, and everything you need to know about the language in order to handle that task better. But let's say there's another task you want to share parameter with, and that task has data sets for that matter. So let's say that you have chunking here, parsing here, part of speech tagging here, and text classification on top of all of them. So you learn from each of them part of the grammar, or part of vocabulary, co-occurrences, relations, dependency trees, and things like that can be useful for you. So this is usually called eavesdropping, when your task does not have enough data to handle all of the feature space that is necessary to handle this task perfectly, and it eavesdrops the other task when it is being trained on its own data, and it learns from that. So one other obvious benefit of that is that you reduce the number of parameters that you have in your network. So let's say 1 million parameters in your network for domain 1, 1 million in domain 2, 1 million in domain 3, and let's say in each of them 500,000 of them goes for feature learning. And if you share all of them, so you have 500,000 as shared, and for each of them, 500 million for each of them. So that number of parameter reduction is enormous. The other benefit of that is that you focus on your task, because now that you have many data from different domains, and it implicitly helps you to learn. When you try to learn from your data, you learn from the part of the data that is more important for your task, not everything general. So you learn general things from other tasks as well, but you start to pay more attention to the things that makes you separate from the other tasks. So it is called attention focusing. The other way is that the other benefit of these networks is that it helps you to augment your data, because let's say for your task, it is like post tagging, part of speech tagging. It is 500,000 data, and you have 1 million data for text classification. And now for 20 your shared features, you have 1.5 million features, training data. That is good. So you have some data for free. And the other thing is that you learn some features for task A. For task B, you have other data, and it helps you to reduce some noises, because each of them has their own systematic noises, and they are canceling each other. So you have systematic noise cancellation here as well. And one of the good things that this multitask learning is helping is that it exploits the relation among tasks. Whether you do it explicitly by fancy architectures that you give to your MTL, or you learn it just by a normal MTL, and it implicitly starts to learn the features from the different tasks. And from this task, I learn this sort of features. From that task, I learn that sort of features. And this is the type of the network that you wish to have. And it helps you to regularize, and it gives you inductive bias, and it gives you representation bias. But there is no free lunch, so you have lots of problems with that as well. There are challenges for multitask learning: the fine-tuning versus generalization trade-off. Whether you fine-tune for one task, the other tasks start to become over-generalized. So your network is overfit in one task, and for others, it's not good. So you have entanglement of private and shared features. So you learn some features for all of the tasks, but you can see that some features in that, it is specific to this task, or to this task, or to the other task. It's not useful for all of them. And you have sophisticated relation among some tasks, and redundancy in emerging feature space. And sample and task orders for training is always problematic, because you don't know what to do. You do it normally uniform sampling or things like that. So partial feature selection, should we use all of the learned features or a part of that? And catastrophic forgetting, when you try to learn something new for task 1 and you forget how to do task 3. And this is the problem. So as I mentioned, in a fully shared network, a classifier only use generic features, and it's shared between all of the tasks. So the task performance would be suboptimal. It doesn't have any specific task, any specific features for the task. And fully shared settings are not capable of capturing this complicated relations between tasks. So in 2007, an architecture is proposed. An architecture is proposed called Private-Shared MTL, that shared some part of the features, but for each task, it proposed to have one specific feature space, that these two together serves as the basis for the task learning, as you can see in the blue one, and the task layers for that, like fully connected layers that are going to use these features. So it has two complementary sets of features that capture some patterns, and it promotes the performance of each task, but it has some challenges. So there is no guarantee that useful and generalizable features emerge in the shared space. The other problem is that some features are better suited only for one or few tasks, not for all of them, as I mentioned in the previous slide. So it wastes your capacity of the feature space, shared feature space. It limits the overall effectiveness of the network, because you could do better, obviously, and it jeopardizes the generalization of these features on unseen tasks. So what do? We need to promote the task-specific features to be in the private feature feature space and for task-independent features to be in the shared space. How we can do that? So we can regularize the private and shared multitask learning by fine-tuning on a task that's without diminishing the performance of other tasks. So we proposed task uncertainty to gauge the effect of the shared features on the other tasks. And the model helps you to not overfit and not underfit. So what type of regularization are we proposing here? Let's say that without regularization, task-specific features will still emerge in shared space, even with this regularization. The other problem is that we have potentially redundant feature space. So we need to propose something that is very effective for that. To maximally improve the utilization of the shared feature space, we need to separate shared and feature space as much as possible, and we need to reduce the redundancy. And this will help us to improve the transfer learning, improve the performance, provide explicit control over the generalization of the shared model, and improve the convergence speed. What if we can use unlabeled data for that as well? That would be very useful. So we propose global task uncertainty discrepancy. So what is this? We monitor how private-only and shared-only features are working for this multitask learning, and it measures the uncertainty between each feature set. So this is the global one. So we, for each task, we make a classifier based on only shared feature space and see that, okay, what is the uncertainty of task 1 only with these features, task 2, task 3, task 4, and we sum them and we get the overall and global uncertainty for all of the tasks only using shared features. The other one, we use only private and shared features for task 1, for only all tasks that we are training at the moment, and see that what is the uncertainty for this task. So we calculate, and for this, because we don't need labels, we can use unlabeled data. Because to calculate the uncertainty, we really don't need the labels. We just want to know that if our classifier will give a very decisive decision about whether it is positive or negative, whether it is 0 or 1. So there is no label needed. Just we don't want it to be in the gray area in the middle. We want to be black or white. And so to these three terms, the task loss, that is giving the overall performance of that task on development set, and the global uncertainty of all of the tasks on the development set, and the unlabeled data and semi-supervised loss that we get here for this specific task. We somehow sum it all together and it serves as a loss function for your network to train, and it disentangles the shared and private features, and it gives you a private push every good thing from private space to the shared space because everyone else is trying to use that, and it punishes it when it's becoming a monopoly, and expels it around it once because it wastes the space and it is suboptimal, and uncertainty is very sensitive to this. So to test that, we use this data set that it has 14 product reviews tasks into 14, the first 14. And IMDb dataset consists of positive and negative reviews for the task, and ML dataset that is subjective or objective. So we used almost 2,000 data, labeled data, and 2,000 unlabeled data for this. And we conduct two experiments. The first experiment is we train our classifier based on all of the tasks. We want to see that how does it perform? Does it have good performance or bad performance? And investigate the effects of proposed uncertainty. And the experiment we want to see how generalizable it is. And we have some competitor algorithms like MTCNN that has partially shared convolutional layers for different tasks, fully shared network, shared private network, and shared private network with adversarial training. And as you can see here, the proposed regularization improves the performance of its baseline in almost all of the categories. And it is not significant, but it almost outperformed the adversarial training for this because we are working for both. And adversarial training aims to push out the domain-specific features from shared space, but the method pushes out the features that are increasing the global task uncertainty and local and reduces the local task uncertainty. For the second leave on out classification, you can see the results are more generalizable, and as if we use it to classify, you can see that it results are acceptable. So as a conclusion, we propose a global local task uncertainty, and it can use the unlabeled data, and it is good for measure the local uncertainty and global uncertainty, and we use uncertainty to disentangle other types of MTL architectures in the future or other metrics, and we can use this semi-supervised learning. And thank you so much for it. Sorry for going over time.
Thank you.